Okay, so this is a very simple experiment. So basic ideas, we discuss few chapters earlier in the semester. Let's talk about very briefly the idea of a circular motion. Uniform circular motion we discuss on chapter number 4, section B, chapter 4, part B. So that chapter we talk about if an object is starting to moving on the circular path by keeping the radius fixed, which means object moving always around this fixed point. Let's say this point is P, and then this is our object. And then now object will be rotating on this circular path. So always this radius is stay constant, and then object can stay on that path only if this R is actually remaining constant. If that is starting to change, or if that connection is not there, then the object is going to go in this tangent direction. Okay, so because of that, we always say object has a velocity along the tangent direction, this word direction, but object cannot move there because it actually attracted to the point P. It can be either physical force, like in this particular case, let's consider this is some sort of string attach the object. Because of that, there should be some sort of string tension force towards that direction. But various chapters you will see later in the semester, that force can be very different depending on the scenario. Chapter 6b, we talk about that force can be a part of normal force when we're talking about the banked angle highway scenarios. And later in chapter number 15, you will see that can be a universal gravitational force if you're talking about Earth orbiting around the sun or things like that. Okay. So the on chapter 4b, we talk about a couple of other things. So mainly this velocity direction all the time changes. If I take a look, couple of other give me 1 minute, okay? All right, guys, sorry about that. Let's continue. All right, so we were talking about this tangent velocity direction. So we assume one thing: the magnitude of the tangent velocity remaining constant, which means magnitude-wise that doesn't have any effect at all, always as a function of time remaining constant. But the direction-wise, if we take a look different places, let's consider point A, point B, and then maybe two other critical locations, point C and D, then you will see that direction of tangent velocity always changes. The directional change will actually generate acceleration towards center always. That we call there on chapter 4b centripetal acceleration, right? So that centripetal acceleration, we found an equation for that. That centripetal acceleration is C, we write R times omega square or V square divided by the R. Omega is delta theta over delta t, which means rate of change of angle. So that can be measured by using radian per second. If I consider the one complete rotation, then delta theta goes to the 2 pi, and then delta t we generally says period of oscillation. One complete rotation means object is starting from A and then go to B, C, D, back to A. one full cycle, okay? So because of that, omega can be rewrite 2 pi over t, 1 over t, which is generally called the frequency. Frequency means how many rotation per second, for example, measured units 1 over second or the unit hertz. And because of that, generally omega can be right 2 pi times the f if needed, okay? Because of all of these, we discussed chapter number 4b, so we can correlate these angular quantities and the linear quantities as needed, okay? So the V, linear quantity, which is equal R times omega, and AC, which is a linear quantity, which is equal R times omega square. Then you will see how the correlation look like. Always linear quantities look like radius multiplied by the angular quantity, okay? So all of those are valid. We talk about those things on chapter 4b. Then chapter 6b, we talk about if there's particle orbiting on this object or orbiting around this circle, the object has a mass, which means I can apply, for example, sum of forces is equal mass times the acceleration at any given moment to this rotating object. Then we can identify there should be a centripetal force every time on this object, similar to the centripetal acceleration direction. If AC remaining always toward the center, then which means there should be some sort of force acting always towards the center. That force, which we generally call the centripetal force, which can be a result of some other physical force. So in this particular case, if I apply the F equal ma to here, you can clearly see negative direction. We have the tension force, which is equal negative direction m times the AC. M times the AC is a centripetal force we generally call. So the centripetal force is always can be originated because of some other physical force. We have seen that on chapter 6b, banked angle scenario, it is part of the friction and part of the normal force. And then we talk about canonical pendulum, it is part of the string tension force. And then right here, it is a string force again. And then in chapter 15, you will see that centripetal force can be a universal gravitational force. If I consider in the satellite orbiting around the Earth, or maybe Earth orbiting around the Sun, and then so on, okay? So that's all of those we discuss in a way previous chapters, okay? And this information gonna needed again chapter number 10. Some of this information definitely this we needed. The idea of this we needed. Chapter 10, this idea we needed again, and then few other chapters. Chapter 11, 12, chapter 11, 13, and then 15. All of those chapters, these concepts needed again, okay? Now let's take a look now the idea of this experiment. We would like to set up some sort of physical experimental setup and then investigate these concepts. That's the plan for this experiment. So which means I need to have some sort of physical setup. So in that setup, I need an object which moving on the circular path. Then we should be able to measure some physical parameters, like for example, mass we can easily measure, not a problem. And then period of oscillation we can physically measure. If I can see object is rotating, by having a stopwatch, we can find the time for one complete cycle, right? That we can measure directly. By measuring those, what we're trying to confirm the concepts we actually build here in chapter 6 and chapter 4b. So to do that, then if these are the physical parameters we can measure directly, mass and the period of oscillation. By knowing period of oscillation, maybe we can find the omega, 2 pi over t. By knowing the omega, definitely we can find the AC because that is equal R omega or V square over R. But that way I cannot confirm anything or I cannot prove anything. I can just do experimental calculation only for this, right? By knowing AC, I can calculate Fc, which is mass times the AC. These three calculations are directly possible by just simply measuring these two parameters. Now let's take a look if I want to confirm or validate a physical concept, then we needed to measure that physical concept at least experimentally by two different methods. Then we can compare the two different methods. We can say this is method number one. If I can measure, for example, f of c by using another physical method, then I can compare those two. If those two exactly the same, then we can confirm all the information, all the relevant background information attached with that physical concept, which means this definition, centripetal acceleration definition, and then everything. Okay. So which means I need to have a setup which needed to have a rotation, and also we need to have another way to measure that physical force. In this particular case, this physical force, centripetal force, is actually resulted due to the tension force. If I can find the tension force another way, then I can easily confirm. That is the plan. Now to do that, we're gonna make a setup look like this. So we're gonna take a string and then we're gonna attach small object like a particle, small object into one end of the string, and other end of the string we can attach maybe a hanger. Hanger can have the slotted weight into that. But I cannot keep these objects like this, because if I try to keep it this way, we can maybe have a small tube right here, and that tube we can hold by using the hand. Then if I try to keep this object, it will not hold there, it will go downward direction because gravity is dragging. However, if I hold this point right here and then start rotating this object on a circular path, this kind of path, which path is on xz plane, this is x-axis, this is the c-axis. Now this green line is on xz plane. So if I can move that object around this path, then you can physically see that object can stay on that circle. We are holding from here this small plastic tube in the middle. Let's consider this is point P, and the hanger mass will stay there without any problem, because that object, that black dot, is moving on the horizontal circle. That horizontal circle is actually sustained because we actually applied some tension force right here, which is the tension force. Everywhere has to have the same tension force. We actually provide the tension force into that moving object by using the hanger weight. As far as hanger weight is there without doing anything, it not moving up or down or anything, that other object, let's consider mass m. Mass m can move horizontal circle on xz plane. So that's our simple setup. So as soon as I stop the motion, you can build this setup, very simple setup in your home. And if I stop the motion right here, or if I not holding that properly or keep doing the rotation, then this system will not stay like that. It cannot sustain any longer. So which means I now need two different things to sustain the system as it is. One is horizontally rotating object must rotate like that, otherwise it will fall down. And then vertical string has to have a mass attached into that, because that force is actually providing the f of t to the horizontally rotating object, which is a centripetal force. Okay. Let's take a look at the free body diagram for this object. Now, if I apply sum of all the forces is equal mass times acceleration into that object, this exact moment, then object has f of t, which is equal mass times centripetal acceleration. This part right here, technically the centripetal force. Centripetal force on a moving object is actually the force of tension. Then if you look here, I have downward direction mh times the g, which is the force of gravity. And this object does not move up or down, it stays there without any motion. Then if you apply f of all the forces is equal mass times acceleration into this object, then I will get f of t, which is equal mh times the gravity. Now, technically f of t is equal centripetal force. Centripetal force we can find by using mh times the gravity, and also we can find it by using mass times the centripetal acceleration. Centripetal acceleration we know, which is equal r times omega squared. Now we can calculate f of c by using two different methods. One by knowing the Hanger mass and the force of gravity. One by knowing the moving object mass and the centripetal acceleration. If I'm getting these two exactly equal to each other, then I can confirm all the concept and the physical principles attached all the way back into the chapter number 4B level. Okay? Because that's where we started all of these, right? So the definition of the uniform circular motion and the proof of AC and the linear velocity, omega, things like that, we first started there. This can actually validate all of those basic concepts and principles. That's the plan. It's a very simple experiment, very simple setup, but it's a very useful experiment because almost all the circular principles, angular concepts can actually validate very easily. Okay. Any question, guys? Any problem? Okay, then let's continue. Let's take a look now this equation a little bit further. Now we know if C is just mh times the gravity, that is method 1. Then if C is mass times the AC I can write R times omega square, and then omega, m times R times omega, which is equal to pi over t. This is going to be 4 pi square divided by t to the power 2. Now this whole thing should be equal to the mh times the gravity. Now, if you look at it carefully here, let's say, for example, there's three variables you can identify, right? Because always we would like to see how many variables in our physical experiment. And then we always like to make a graphs and things like that to see how the variables relate to each other and behave each other. So in this particular case, G is a constant. Let's consider we keep mh constant at this point, 4 constant, pi constant. Let's say R is constant, then I can find easily the two variables, right? So if my two variables are m and t, I can take the t square one side, bring everything else into the other side. R times 4 pi square divided by mh times the g times the mass of the moving object. Now, we can take a look by keeping all of these constant, how the mass of the moving object is actually related to the period of oscillation. If I change the mass of the moving object and then put that into x-axis and then observe how the period of the oscillation changes as a function of mass changes, then I should see y equals slope times the x type of equation. So which means I should be able to see a graph look like this. This is going to be t to the power 2. This is going to be mass of the moving object. The graph will be look like this. Slope of the graph should be equal to this whole part. R times 4 pi square divided by mh times the gravity. By knowing these parameters, I can predict the slope. Then I can compare that. Or by using the slope number, we can maybe calculate some other parameter. For example, mh. From this equation, we can calculate the hanger mass. Then I can compare that with the mh known value. If I'm getting exactly the same answers for these two, then we know all the information we used, concept and principle we used are actually true. Correct. Okay. That's our part B. And then we can extend that picture a little bit further by selecting the different variables. Because if you look this equation, we can identify four variables. One is mass, one is radius, one is the period of oscillation, one is the m of h. Technically, if I consider period of the oscillation is our y-axis or the dependent variable, then for independent variable, I can use either m or r or m of h. Any of these at any given moment, we can put it into the x-axis. So as a result of that, we can investigate same by using the same setup, at least three different variations. One is t versus m. Then we can check what happen if I do t versus r. Then we can check what happen if I do t versus m of h. So three different variation we can investigate by putting t, always going to be the period of oscillation, which basically changes itself if I change any of the other three variables. Okay. So that's the overall picture and the plan for today's experiment. Any question, problems? Okay, then let's continue. I think in terms of lab report, this is going to be your last lab report, I think. Um, these six lab reports should, out of these six, five only should be done. Okay. So I think by now, most of you probably done five. If that is the case, then you don't need to do this one. But make sure at the end of the semester, five must be submitted. Okay. Uh, since this is assigned as a group report, I will put you guys into maybe like two-member or three-member group, but talk to your peers and then arrange everything if you're planning on doing the group report. Maybe other group members not maybe even willing to do the group report. In that case, you have to do individual report. Okay. So talk to the group members. I will put you guys into the breakout rooms at least 3-4 times. Then during that time, discuss those things too. Okay. And a couple of other things I want to point it out very quickly. I think all of you guys are doing fine. You may needed to take a look the grade book. This is, I think, several times I mentioned this over last few weeks, but I want to reiterate this again. Take a look the grade book. By now, ICQs, which are in-class quizzes, and three lowest grade are dropped already, okay? Which means whatever the number you see after that drop happen, you have to be careful. Three more to go. Usually those three are easy. Since everybody now know how to study for this class, I think should not be a difficult thing at all. It's based on the people, person to person, it can change, okay? And if you get more lower points in next tree, one of the next tree, then that can still affect your ICQ point. It's a lot of points, about 40 points, okay? And in the lab report, one lowest grade already dropped, which means uh, make sure 5 out of 6 must be done in terms of lab report. So if you have a 0, 1 0, it is fine. But if you have more than 1 zeros, those will be counted. So that will be a problem. Okay. So make sure by the time of the end of the semester, 5 should be submitted. Because if you want to just not submit one, that will be automatically the drop lab report. Okay. And for ICQs, we're going to be doing 13. Out of that 13, 10 will be counted. So make sure you definitely do 10 or more. Otherwise, any of the quizzes you miss will be automatic 0. So those will be automatically the drop quizzes. Okay. Other than that, everything else in this class counting for the final grade. So take a look at the grade book right now. It is out of 72. So if this your number, I think most of you guys fine. If your number is greater than 50, you are fine. But if not, then you can stop by and then talk to me. I can take a look individually, case by case basis. If you in below 50 means right now, you already losing 22 points. It's very unlikely to catch up that and then get even 70, I think, at the end of the semester. Okay, that will be very tough thing to do. Take a look and then talk to me if you have any question or concern about it. Okay, any question, any problems? Okay, then let's continue. So our lab manual has a simulator link. Let's take a look at that. There's a typo here. It should be experiment number 9. So don't worry about that too much. And all the theories we just discussed there. This is our simulator link right here, which is a very simple simulator. Let's move into that one. Initially, it should look like this page. There's a begin button to the right-hand side corner. Just click on that. Then you will see the simulator for today's experiment. That's it. It's a very, very simple experiment and simple setup. The real life experiment is a little bit challenging than this simulated experiment because real life experiment has apparatus which has a rotator in the middle uh, like a real life motor, which is actually in the middle of a box, and then which can align into vertically up, and then I can attach, like for example, the string into this point. Then when I switch on, this rotor will rotate really faster, and then the string gonna go into that horizontal circle. So a little bit challenging means not that setup. Setup is very simple, but it's challenging because it can be very dangerous because we have to do certain arrangement and then look very carefully close by. When you go close to that apparatus, if that rotating one rotate really faster real life setup, like maybe 400, 500 rotation per minute, it's a really high speed. If somebody go much closer and then have a connection like the face area or maybe hand into with the object, that will be very bad, very dangerous. It can do a lot of heavy damage. Okay, uh, but this simulated experiment is very, very simple compared to that one. So that's only the difficult part if it is a real life setup. Otherwise, everything we do like little bit more aligned with that. There are little bit of changes. For example, this vertical string is not there. Instead of vertical string, that part is actually a spring attached to that same setup. So we need to find the centripetal force by taking the spring off and then doing the Hooke's law experiment separately. Okay, so basically inside this experiment, we doing the two experiments simultaneously. Okay, so that's the only difference. Other than the basic concept, going to be very simple and same. So that's about it. Then let's continue. Let's take a look what we have in the simulator. Um, we have a string, which I mentioned earlier right here, horizontal one attached to the black dot. And then there's a small red color piece is the tube. And then that should be held by the hand. And then other side of the string goes down and then attached to a mass hanger. And I can change the mass hanger amount of mass. In this case, this number of washers, you can see now, I have 7, you will not see exactly the same number. That's okay. You bring your cursor on top of that washers, start doing the clicking, then the number of washers will change. So maximum, I think we can go maybe like 30, 35, minimum is 5. In between numbers, you can bring different numbers by clicking, okay? So I'm going to start somewhere like 10, but it's not required you to start exactly same number. Whatever the number you can get somewhere around 10, you can start there, okay? Nothing to worry. Whatever you see, you write it down. You will still get the right answer, okay? Then this object cannot stay like this, right? This black dot, it's going to fall down. I have to continuously rotate that. The rotation will start when you click the start button. So you can see now object moving on that horizontal circle. as far as I doing that motion by holding the red tube on my hand, then object can stay that motion. Okay, you can physically do this kind of setup very easily in your home. And if you take a look now, what we like to measure, masses we can measure very easily. Moving object mass given here. What we really trying to measure is the period of oscillation, which means I need to start and stop when it complete the one cycle. Let's try to do that. Start. When it come back to the same location, I need to stop. It seems to be a little bit tough to do that. Start, stop. You can see the period of oscillation already like about 1.4 second or less. So it's a little bit difficult and challenging to do that. Because of that, we're not going to do one period of oscillation. We will let it rotate maybe like 5 times, and then we'll take the average of that. And then we will repeat that uh, each time, each case for at least 3 different times. Okay. So that's why you can see on column C right here, for each particular mass of the object, we're going to take the period of oscillation 5 cycles 3 times, totally 15 oscillation. Then we'll add these 3 together, divide by 15, we can find the period. By doing that, what we're trying to minimize is the human error. Even though this is a simulated experiment, there is a human error part now, because I need to click and then it's click again to stop. So which means that reaction error can generate the error. Okay, so that's important to minimize as much as possible. That's it. It's very simple setup. Mass of the moving object can change by using these arrows. I think minimum all of us can go down to 25. When I click the up arrow, you will not get the my numbers. Every time you use this setup, you will get a different numbers. Minimum point and the maximum point gonna be the same, but in between numbers can be random. Okay. So I'm gonna start the minimum number. Radius, when you starting the simulator, it usually should be around 200 centimeters. That's a little bit different meter ruler here, 2 meter long meter ruler. Keep that for first part. Later we'll change the radius. Okay, there's a way to change the radius. I will show you that. It's very simple. So that's it. So now what we're trying to do, we try to investigate those 3 independent variables: mass of the moving object, radius of the circle, and the number of washers in this particular case, which is the hanger mass, how those 3 independent variables are affecting to the dependent variable, which is a period of oscillation. So as a result of we changing those 3, you will see period will automatically readjust as it needed to keep maintain this rotation. Okay. All right, guys. Any question, problems, any concern? Okay, and I forgot to mention one quick thing earlier when we're talking about the grade book. There are no any particular extra credit or anything. There are a little bit of extra credit in terms of surveys. I will give you this specific, maybe like after next week, probably, I will open some of the surveys which are for me, and then one survey will appear from the Bergen, our college wise. Okay, you complete all the surveys. Each survey gonna have about like 0.5 point to your final exam grade, not the final grade. Okay, final exam grade. But that is very useful. Sometimes not the people who are having the lower grade who having the higher grade, but in between the margins, like somebody have like uh, 88 or 89, maybe he can jump into A by just using those extra credits. And then somebody has maybe 78, 79, 79.2, then easily can jump into B and then so on. Okay. It is useful, but it's a very small amount of grade. And then one other thing I forgot to mention: if any of you are in right now in like 60 to 70 region, then you can stop by and then talk to me. I want to take a look individually where you losing the points, and then we can take a look whether there's a chance to improve that to get finally C grade. Okay. As I remember, all of you guys are above that level, so you should be fine technically. All right. So, but anyway, just take a look that and then stop by if you have questions. Okay. All right. So let's start this. Let's start to investigate this rotation as a function of mass first, mass of the moving object. So table number 1. So the hanger mass, we're going to keep it constant. I have a number of washers 12. So each washer is about 0.01 kilogram. Each washer is only 10 grams. Okay. So to get the total mass, I have to multiply 12 by 0.01. And the radius, I'm going to keep it 2 meters at this point, 2.0. 0 in meters. I cannot have the decimals in this particular meter ruler more than 2. The reason, if you look at it carefully, that meter ruler, it has 200 centimeters, and then in between each 100, it has only 10, which means each of this small line is 10 centimeters. So the minimum value we can estimate is 5 centimeters. So the error with this meter ruler is going to be really, really large. But that will not be a big deal because it's a simulation. It will give us this moving object a line nicely with some black line. When I'm measuring the radius, you have to measure starting from this 0, a line with this vertical orange line, to the mid of the black dot. So the mid of the black dot should align with one of the black line on the meter ruler. Okay. Right now it's 200 centimeters, but we need that unit in meters. Centripetal force we can calculate by using the hanger mass. It should be hanger mass multiplied by the force of gravity. Hanger mass, which is 12 times 0.01 times gravity 9.8. Then I can have unit Newton. You need to do that calculation and then check that number. Okay. Let us check it out that very quickly. I have 12 times 0.01 means 0.12 multiplied by 9.81. So we should get about like 1.1772. Okay. 1.1772 in units Newton. Okay. So that's our centripetal force we providing now to the rotational object. So by measuring the oscillation time, I should be able to calculate that. That's the plan for this part A of the experiment. All right, let us start that with the moving mass 25 grams, which means divide by 1000, it should be 0.025 kilogram. So we would like to measure period of oscillation. Since it is a small number, we're going to try that for 5 oscillation 3 times, and then we will add everything, divide by 15 to get the period of oscillation here. So let's do that. Now make sure the object is starting right hand side corner, it completing one cycle when it comes there. That is once rotation, 2 rotation, 3, and then 4 and 5. You have to count the 5 and then stop the time. Okay. Start, count 5. When it is completing the 5th one, stop. Okay. My time is about 6.5. I can do only one significant figure there. I should not have anything more than that. One decimal place there, 2 significant figures. Make sure you get rid of anything unnecessary. When you report in the data, we cannot report anything more. Okay. But after we calculating here, we can keep 1 or 2 extra. Let's check this again. Okay, 6.6. So that's a human error, right? So it seems to be consistent. Seems to be very consistent, 6.5. Then we'll add these three together, sum of all of this tree, and then divide by 15. So that's the period of oscillation, about 1.307. That accuracy is much better than what I'm trying to see directly, because since it is a calculated value, we can keep 2 more extra decimal places, okay, at this point. So now this is the period of oscillation, which we get from the calculation. They add the function just below the table, okay? Then all the rest is just simple calculation. So let's do that. So T square we need, because remember I mentioned that we would like to see this in terms of graphical picture. That's why. Otherwise we don't need that at all. So we can take this and then take the power of 2. We can add that function right here. And then let's do omega. Omega unit is radian per second, equal omega is 2 times pi pi open and close bracket divide by period of oscillation. We'll add that function also just below the table. All right, then we'll do V. Technically, we don't need the V. We can do the calculation by using omega AC. But to get some more idea about, we will calculate the V also. And then we'll use the V to do the acceleration centripetal. But it doesn't matter. You can directly do if you want to with the omega. You will get the same answer. Okay? V is equal R omega. R in this case remaining constant 2 times the omega we calculated here. And see omega represent actually how many number of circles, right? So per second. So that's a really how much the radiation changed per second. So that actually really considerably large number. Okay. This is tangent velocity v, and then let's do a by using the tangent velocity to the power 2 divided by the radius. You can see the centripetal acceleration, which is a really large number. Okay, so a of c, which is really large number, that makes sense because the object is moving really faster. That's why as more faster it moves, more centripetal force towards the center. All right, so let's take a look at the centripetal force by using the centripetal acceleration. Mass of the object, 0.025 multiplied by the centripetal acceleration. Now, if you take a look at that number we already know in a way earlier by using the Hanger mass, right? Because the Hanger mass providing that. Hanger mass provide 1.1772. I have about 1.156. That looks good, close by, but the error margin a little bit higher there. The reason the error is there because of just this observation. We have a fairly considerable human error attached with that observation, because I have to click to start, click to stop when it exactly completing the circle, 5 circles, but there error because I can't exactly stop where it started with. So that error still plays a huge role. Okay, if I try to do 1 circle, error going to be even more high. Okay, then we'll compare those two by calculating the percentage difference. That's it. It's a very simple experiment. Any question, guys? (1.1772) divided by the average and multiply by 100. So it's not super bad. 1.8, about 2%. Considering all the errors we have, that actually fairly very decent error value. Make sure you get rid of the decimals and then show only like 2 visible significant figures. Okay. All right. So any question, any problems? consent. Okay, then I will put you guys into the breakout rooms, and then we'll take 10-15 minutes to complete this whole table, and then we'll come back and then discuss the next part, and then we'll continue likewise. Okay. And make sure you talk with your friends if you're planning on doing the group report. Otherwise, even you go into the group breakout rooms, you are fine. Okay. Let's do maybe 3 groups. Let's add all of these, all of this tree, and then we'll divide by 15. So the period of oscillation is about 2.3 now. And then we'll check it out, the centripetal force, by using this. I need the t to the power 2, this number to the power 2. Let's add this function as we proceed. This should be for the t, and then this is for the t to the power 2. It's about the same function like the previous table, but I need to add each different function in the table. Okay. Then let's do omega v and AC. It's going to be radian per second. It's going to be meter per second. And this should be meter per square second. And the centripetal force should be unit Newton. And we'll compare that with the expected value. So the percentage sign I'm going to leave it here. Okay. Omega, which is 2 times pi divided by the period of oscillation. Much different than the previous because the moving mass is different and the radius is different now. So which affected to the oscillation overall. And then the v is the tangent velocity, which is r times omega. R is now the cell number B55 multiplied by the omega we just calculated here. And then by using that, we can calculate centripetal acceleration, which is v squared divided by the r, about 4.66. By knowing that, we can calculate centripetal force, which is mass of the moving object now fixed 0.250 multiplied by centripetal acceleration calculated experimentally h55. So that number should be still about the same like we got in last time. The reason the hanger weight we did not change. Because of that, from the hanger weight we expecting about 1.177. We getting here 1.165. So that very close by numbers. So our primary goal is actually achieved because we know now all the concept and then principle we used to understand the circular motion is actually true. Okay, that's the idea. Let's compare this to ABS, the expected value 1.1772 minus the calculated value, divide by the average between expected and the calculated, multiply by 100. So it's fairly very small number. I'm going to get rid of the unnecessary decimals. Going to keep only two visible significant figures. Okay, that is the PD. All right, guys. Any question, problems? Okay, then let's continue. You can change the radius maybe by clicking the flag one time or two times. Make sure it visibly changes. Okay, if I click one times, you see it changes only like very small amount, 10 centimeters also, that okay. But when we looking at the period of oscillation, it might not be visible enough. So try to change like maybe 20 centimeters at a time or more. And we need like 4 more data points before we reach the 200 centimeter point. Okay. So let's go back to the breakout rooms and then you can work together to complete the table number 3. Any question, problems? There's no any big difference from the previous part to here. Centripetal force we calculated by using two different methods experimentally. Centripetal force mh times the gravity, and also it can write m times the AC. AC we wrote r times omega square, which means 4 pi square divided by t to the power 2. Then in this particular case, we are changing the radius, and then t will be changed accordingly, right? Then it should be look like mass of the object 4 pi square divided by m of h times the gravity, and then radius. Now this will be the slope of the graph. This is the y-axis, this is the x-axis. Now we'll make a graph between the radius and t to the power 2. Insert scatter plot, and we'll make a graph t square versus the radius. From that we can find the image again. Okay, select data, and x values should be the radius values on table number 3, column B, and the y values should be t to the power 2, table number 3, column E. Click OK, click OK. And it's nice linear graph. We'll do the little bit of formatting. Axis title and the trend line. Then we'll click the trend line options. Check, it doesn't allow me to select the trend line. Okay, should be good. I think trend line options. We'll click all of those three options because we would like to see R square and the number in front of the X, because that number in front of the X we can use to calculate mass of the hanger. That's the plan. Okay. All right, now we'll modify a little bit this. Check why it does not allow. Okay, and the axis chart title, which is t square versus radius, and the x-axis, which is radius, unit meters, y-axis t to the power 2, unit second to the power 2, and by slope we can check it out, the mass of the hanger. And still mass of the hanger we keep in the same. I keep about the same number, which means 12 number of washers multiplied by 0.01. So that will be about 0.12. And from the graph, we need to calculate that. We'll write it down, the function that should be mass of the moving object 0.25 times 4 times the pi to the power 2 divided by open bracket 9.81 multiplied by slope of the graph 8.4887 and close brackets. So I should get about the same number like we got earlier, very slightly off, otherwise it's about the same number. Okay. Let's add those functions here. Let's see, is the mass known value? M of h known value, and it's going to be m of h calculated from the slope. Okay, from, we can say, graph, and then we'll compare those two. Any question, guys? Then it should be about like very small percentage. Okay, we do in PE because we know exactly the total mass on the hanger. Okay, any question, problems? All right, then let's move into the last part of the experiment. In this last part, we would like to change the mass of the hanger because now you know there's three variables, independent variable, mass, radius, mass of the hanger, and the dependent variable going to be the T, right? That's what we decided in the beginning. And then these two we tested out. And then we'll check this one now, mass of the hanger. Now, when I change the mass of the hanger, one important effect immediately you will see, because the centripetal force we providing by using the mass of the hanger, centripetal force will starting to change immediately. That's immediate result we should be able to see. That is no longer constant. Okay, data point by data point, that will change. Earlier two data sets, if you look at the FC calculated about the same, and then FC calculated about the same because we're keeping the mass angle constant without any effect. Now we're going to do that change. Okay, so let's check it out again, one data point first, and then I will put you back uh, into the breakout rooms, then you can complete the table. Okay, so let's radius doesn't matter, the radius value. I'm gonna keep it here. This is about 1.8, close to 1.8. You can estimate that into maybe 1.7, probably. That also okay, because it's in between 6 and 8. Otherwise, you can try to change that all the way to the largest possible radius, which should be 200 centimeters or 2 meters. Okay. If you can get it into 2 meters, that should be fine. Sometime it will not go back automatically into 2 meters. If you want to really do that, you can reset the whole web page. Then it will go back to 2 meters automatically. I'm going to keep maybe the lowest mass for this case. And the hanger weight, I can start from the lowest value. And then I will slowly change the number of washers by clicking twice, okay, at a time. Radius do not change. Moving object mass must not change. I'm going to keep the lowest mass for that one, largest radius possible. And then washers, I'm starting from 5. That's the smallest possible value. Then you click twice at a time to collect the data set, okay. So the radius will keep at 2.00 meters. Mass of the moving object I'm keeping at about 0.025 kilogram. Then the hanger mass we will calculate on next table, but right now number of washers are 5. Make sure you get rid of any decimals because it's number of washers. So it should be just a whole number, okay? Then you take that number, multiply by 5, multiply by 0.01, you will get the mass in kilogram, okay? From last two table number 5 and 6, you cannot click and drag anything downward direction. Table number 5 is fine, particularly table 6. Remember, table number 5 has a merge cell. Because of that, if you do select a cell here, do the calculation in the next one, you still cannot click and drag here, okay? Because the previous one has a merge cell, it will not do automatically the calculation here. Be a little bit careful with that. So this is going to be in units kilogram. And centripetal acceleration calculation we can do by knowing period of oscillation. To do that, we need to measure the period of 5 oscillation again 3 times, similar like we done for last 2 cases. Okay. So let's check it out. Start. About 10.1 second. Make sure I can have only one decimal place for this one. Period of oscillation direct measurements from the simulator. about the same. Let's check it out one more time. Exactly the same. There's no difference at all. By knowing that, I can calculate time for one oscillation, sum of all of this tree, divide by 15. That we can keep a little bit of more sig figs like we done for earlier. Let's add that function here. And then we'll do the omega like we done earlier, radian per second. That's going to be 2 times pi divided by the period of oscillation. Let's add that function also here. And let's do the VNAC. Equal R, we are keeping fixed 2, and the omega we just calculated. That function here. And then we'll do the AC, meter per second squared. That is V square R or R omega square, both are fine. We'll add that function also here. All right, guys. Now, by knowing those, all of those, we can check now centripetal force, because now centripetal force changes for each case by case basis. Okay. Centripetal acceleration we just calculated earlier, and you can copy paste that number, this number. When you copy pasting, make sure you copy, and then when you pasting here, paste as numerical values. Right click, paste option, second one, as a numbers only. Okay. And then get rid of unnecessary decimals. Keep like maybe 3 decimals, okay, but not anything more than that. Okay. And then we'll calculate the centripetal force by using two methods now, by using the centripetal acceleration and by using the Hanger mass. By using Hanger mass, which is equal Hanger mass we calculated on cell B123 multiplied by gravity 9.81. We'll add that function below here. This is f of c by Hanger mass. Then let's check that by using the centripetal acceleration, which is equal mass of the moving object 0.025 times the centripetal acceleration c123. So we expecting this to be about the same. Don't keep too many sections. Okay, about 4 is fine, not anything more than that. That exactly we getting about the same number. F of c from A of c. Okay. Then we'll compare those two. There's no any standard value or anything, so we'll do in the comparison in terms of PD. Equal open bracket ABS, difference between the numbers divided by the average between the numbers. Okay. Any question, guys? Any problems? All right, now when you bring in the numbers from the table 5 to 6, make sure you bring one by one, particularly for these two columns. Do not try to copy paste everything because it has a merge cell. It will not properly come into here. Okay, copy paste one at a time, and then the rest right here you can easily do by clicking and dragging. So that's our last part. So we'll try to complete that maybe 10 minutes, 15 minutes max, and then we'll come back and then continue into the chapter 9 part B. At least we'll start the discussion, major part of that chapter, and then we'll continue that on this Thursday. Okay, that's the plan. Any question, problems? All right, then I will put you guys back into the breakout rooms. Also talk to your peers if you're planning on writing a group lab report, okay? Move into the, there's nothing much to do in this lab. Lab is done. Okay, we will start.